In this video, I hope to illustrate a beautiful example of a pair relationship in math, involving the Stirling numbers. Stirling numbers are basically these two-dimensional tables of integers that extend downwards infinitely. We typically use n to refer to the row number and k for the column number. They come in two kinds: Stirling numbers of the first kind and Stirling numbers of the second kind. They can either be unsigned or signed, where every other diagonal is flipped negative. But where do these numbers come from? How are they calculated? Why does it matter? They have several equivalent definitions, so let's start with our first one, but it first requires a little bit of terminology. Define the falling and rising factorials as such. In the case of falling factorials, it looks like we are taking a factorial, multiplying numbers going down, but we stop once we have multiplied n of them. For example, 7 falling factorial 3 would be 7 times 6 times 5. The rising factorial is similarly defined, except the numbers go up instead of down. So 7 rising factorial 3 is 7 times 8 times 9. The reason we care about falling and rising factorials in the first place is because they are deeply connected to a more fundamental counting structure. Combination numbers n choose k, the number of ways to pick k objects out of a total of n. Notice that if we write out the formula for n choose k, we can write it in terms of the falling factorial. If we treat n choose k in the falling factorial as a degree k polynomial, then we can even define negative n choose k. Pull out a -1 from each factor, and write these numbers in terms of rising factorials as well. Here are the identities side by side. We can now define the Stirling numbers. Suppose we took a falling factorial and expanded it out in terms of powers of x. This means that we can convert a falling factorial into a linear combination of powers. If we collect these coefficients, they give us the signed Stirling numbers of the first kind. Now, instead, let's reverse this process and write powers as linear combinations of falling factorials. Now if we collect the coefficients, we instead get a row of Stirling numbers of the second kind. However, notice that this time these are unsigned. If we had used rising factorials instead, notice that the Stirling numbers of the first kind would be unsigned, while the Stirling numbers of the second kind would be signed. So in other words, Stirling numbers are related to the coefficients when we try to convert an expression in terms of polynomials to an expression in terms of rising or falling factorials. So now that we know what these Stirling numbers are, we have a little issue. Computing these values naively through distributing and solving systems is very tedious. Is there a faster way to compute them? It turns out that one of the fastest ways to compute them is to use these two recurrences. These very closely resemble the rule that forms Pascal's triangle, the rule that makes Pascal's triangle very easy to fill out. Except one has a factor of n, the row numbers, and the other has a factor of k, the element number. Notice that these recurrence rules produce the unsigned Stirling numbers. If we want the signed Stirling numbers, you can either just tack on the sign after the fact, or use these slightly modified recurrences instead. Easy. I'll demonstrate how easy it is by using them to fill out the first few rows. While you're watching this, I should mention that there are simple algebraic inductive proofs of these recurrences. However, they are fairly dry and don't particularly illuminate many interesting ideas, so instead I will be presenting a combinatorial proof. This would mean that we need to give second combinatorial definitions to the Stirling numbers, and then prove that they do in fact line up with our first definition. Let's begin. First, let's talk about what Stirling numbers of the first kind count. Unsigned Stirling numbers of the first kind count the number of permutations of n with k cycles. I'll denote this as c of nk, where the c stands for cycle. What does this mean? Suppose we took the numbers 1 through 7 and rearranged them in any order, labeling their positions above. This ordering of the numbers is a permutation of 7. Now, starting from position 1, find the corresponding permutation element, then go to its corresponding position, then go to its corresponding element. Continue doing this, collecting all of the permutation elements. Eventually, you will end up back where you started, and that's why it's called a cycle. Find all of the cycles in this permutation, and put each cycle in parentheses, and you have what is called cycle notation of a permutation. We can see that this permutation has 3 cycles, and so this is a permutation of 7 with 3 cycles. An important detail we should mention now is that this cycle notation is not unique. Even if I were to rotate the values in the cycle, it would still be describing the same permutation. To fix this, let's rotate it until the highest number is in front. However, the order of the cycles can still be rearranged, and we would still be describing the same permutation. Let's list our cycles by their first element from least to greatest. Now, if our cycle notation follows these 2 conditions, it will be unique. This is called the canonical cycle notation of a permutation. Not only is there only one way to write a permutation in canonical cycle notation, but each permutation in canonical cycle notation only ever points to a single permutation. So now we want to prove this identity here, which tells us that these numbers form the coefficients when the rising factorial is expanded. For example, if we were to write out every permutation of 3, then write each of them in cycle notation, you can see that there are 2 permutations with 1 cycle, 3 permutations with 2 cycles, and 1 with 3 cycles. This means that this identity should hold, and if you expand, you'll see that it is true. Proving this in the general case will demonstrate that our combinatorial definition lines up with our first algebraic definition. We will now prove this identity by double counting, meaning we solve a particular counting problem twice, in 2 different ways, so the answers must be equal. In this case, the counting problem is, how many ways can we have a permutation of n where each cycle is colored with one of x colors? For example, here is a permutation of 4 with 3 cycles. If we had 3 colors, we could color the cycles like this, or like this, or like this. Note that we are allowed to reuse colors. The right side is pretty straightforward. Suppose we are looking only at the case of permutations of 4 with 3 cycles. There are this many permutations, but for each cycle, you have x choices for colors, so in total there would be this many ways to do this. Now add all of the cases for any amount of cycles, and you get the right side. Now let's do the left side. Let's add the numbers from 1 through n to our permutation one at a time. First we add 1, and it must go in a new cycle. Since it is a new cycle, we need to give it a color, and we have x choices. The next number we include, 2, now has 2 cases. We can either make a new cycle, which once again gives us x choices, or we can place it in an existing cycle. Here, we have 1 choice to place it. Placing a number at the beginning or end of a cycle is the same, since the beginning of the cycle is the end of the cycle. This gives us a total of x plus 1 choices for where to place the 2. We add the next number in the same way. There are 2 choices this time if we add it to an existing cycle. We can place it here after the 1, or here after the 2. We will need to rotate the cycle to put it in canonical form, but both of these positions will give unique permutations. Or, we create a new cycle and have x choices for colors, which gives us a total of x plus 2 choices for where to place the 3. And so, if we continue this process, the number of permutations with colored cycles is x times x plus 1 times x plus 2, etc. 1 factor for each of the n numbers, which is simply the rising factorial. Now that we have this identity being true for rising factorials, we know that the identity for signed Stirling numbers of the first kind also holds for falling factorials. To see why, observe how distributing the falling factorial works. When we distribute, we choose 1 term from each binomial, multiply them together, then sum up all of the possibilities. The only difference with the rising factorial is that whenever we don't select an x, we select a negative factor, which flips the sign. So now we know that Stirling numbers of the first kind, which count permutations with a certain number of cycles, form the coefficients when we write falling and rising factorials as polynomials. Now let's do Stirling numbers of the second kind, which convert back the other way, converting polynomials to falling and rising factorials. Stirling numbers of the second kind count a certain kind of partition, and I'll label this counting function as b. How many ways can we partition n distinguishable objects into exactly k indistinguishable boxes? For instance, if we have 3 objects in 2 boxes, here are all of the ways to do this. We can't include this choice here because the boxes are indistinguishable, so these two are really the same. We also can't count this possibility because we can't have empty boxes. The identity we are trying to prove is this. Once again, let's tackle it with a double counting proof. The counting problem we will use is this. How many different ways can we place n distinguishable objects into x distinguishable boxes? This time, the boxes are in fact distinguishable, and they can even be empty. The left side is easy. For each object, you have x choices for which box to put it in. So this is just x times x times x, etc., n times, or x to the power of n. For the right side, once again let's focus on a single term first. Suppose we have 4 objects that go in exactly 3 indistinguishable boxes, and they must be assigned to 5 total labeled boxes. First, we pick one of the ways to assign 4 objects to 3 indistinguishable boxes, one of the b of 4, 3 ways. To create one way to assign these 4 objects to the 5 boxes, all we need is to assign each of our unlabeled boxes to one of the 5 labeled boxes. The first box has 5 options, the next box 4 options, and so on and so forth, for each of the k boxes. This is simply the following factorial. All we need to do now is add up each case for every k value, and this will cover every possible number of non-empty boxes. Once again, we have a related identity, with a rising factorial instead of the falling factorial. It is relatively easy to see that this identity is true by simply using what we figured out about the signs of Stirling numbers of the first kind and expanding them out. Okay, now that we have proven these identities, we know that these counting definitions line up with the first algebraic definitions. Now we just need to prove that the recurrences work. Once again, here are the recurrence relations. Let's start with Stirling numbers of the first kind, which count permutations with a certain number of cycles. How many permutations of n plus 1 have k cycles? Let's look at an example where n equals 4 and k equals 3. On the left side, we want to count the number of permutations of 5 with 3 cycles. This problem can be answered by splitting into 2 cases, where n plus 1, in this case 5, is either in its own cycle or not. If 5 is in its own cycle, we just ignore it and look at the rest of the cycle notation. This is simply the number of permutations of 4 with 2 cycles. If 5 is not in its own cycle, we can start with a permutation of 4 with 3 cycles, and notice that all we need to do now is slide the 5 into the cycle notation somewhere. We have a total of 4, or in general, n different ways to do this. And so, if 5 is in some cycle with other numbers, there are n times c of nk permutations. Now let's do the recurrence for Stirling numbers of the second kind, which count partitions of distinguishable objects in indistinguishable boxes. This one is pretty much the same idea. We will take b of n plus 1, k and split it into 2 cases. Either n plus 1 is in its own box or not. If n plus 1 is in its own box, then we just ignore it, and that's just b of n, k minus 1. If n plus 1 has to be placed in some box, then we can put it in any of the k boxes, so that's simply k times b of n, k. And that's it. We now know not only why these numbers allow us to convert from a polynomial base to a rising or falling factorial base, we also have easy ways to compute them. By simply plugging values into the recurrence equation, we can build the rows of Stirling numbers easily and quickly. So now we have seen the inverse relationship between these Stirling numbers. Initially, they may not look related at all. One counts permutations with certain numbers of cycles, one counts partitions of distinguishable objects in indistinguishable boxes. However, we have seen not only parallels in their recurrence relations, but they also allow us to convert from powers to rising and falling factorials and back. So now the question is, if there are so many parallel relationships between them, how come their combinatorial classes look so different? What is the combinatorial thread that connects these two ideas? It turns out that this can be pretty straightforward. Notice that if you take a permutation's cycle notation, which is what the Stirling numbers of the first kind are counting, and treat all of the numbers in a cycle as just the objects that go into a box, this is almost exactly what the Stirling numbers of the second kind count. The only difference is that the cyclic order of the objects in the box matter. This also helps illustrate why one recurrence has n and the other k. Notice that the parentheses in canonical cycle notation can be completely ignored because we can recover them by simply finding a new cycle when we find the highest number so far in the permutation. And so there are n places to inject the next element without making a new cycle, one for each element in the permutation. We can't place it on the end, because in canonical cycle notation, this would add a new cycle. On the other hand, regarding the partitions, we can standardize the order of the elements in the boxes the same way we did for canonical cycle notation, by writing the elements in decreasing order. We notice that if we must place the new element in a box, it must go in the front, since it's the highest value. This gives us k places to inject the next element without making a new box. So what's the lesson here? Hopefully, this video clarified the motivation and definition of the Stirling numbers, as well as proving some important key properties, in a way that shows their connection to combinatorics. In addition, these methods should also illustrate the natural pairing between the Stirling numbers of the first and second kind, in ways that were likely not very obvious at the outset. The combinatorial classes of these numbers, the permutation counts and partition counts, really don't feel like they have anything to do with each other, and yet they are so intimately related. One of the things that makes combinatorics so mysterious is how seemingly totally unrelated classes of counting problems can have such deep ties to each other, and sometimes these mysteries run unimaginably deep, connecting areas of math we never thought possible. What could be more pure and straightforward than counting? And yet, its simplicity and concreteness is what makes uncovering its essence so difficult and elegant at the same time. If you appreciate my work, please like, subscribe, and share this video. If you would like to support me, feel free to subscribe to my Patreon or head over to my AbleBeast profile to petition me for more math content. Keep in mind that you won't be charged unless I deliver the content, so there's no risk to you. Thanks for watching, and I'll see you all next time.